All right, hello again. This is the 6th media computation video. This one is really about media computation, so we're picking up a lot of that. We've already got a lot of the Java that we'll need, and we're just going to be making lots of interesting looking pictures. So let's get started. And we'll change focus and do here. So what we're going to try and do today is we're going to try and learn how to manipulate images. We're going to write a couple of methods. We'll talk a little bit about testing and debugging, although that will come again later when we're talking about classes. And we're going to talk about grayscale, luminance, and black and white pictures. So let's keep moving. So one of the first questions is, when you write a program and you execute the program, how do you actually know if the program worked? Or even better question, how do you know what went wrong if it didn't work? So a very important part of programming is testing the result. As you have no doubt seen by now, just because the code compiles and seems to run doesn't mean that it actually does what you wanted it to do. And so that means there's usually an error in your logic. It's a misunderstanding in your part of the algorithm that you're using, or it's a misunderstanding of how the problem is supposed to work, or there could be bad data. There's a lot of different ways that your program could actually compile and run but not give you the right answer. Let's talk a little bit about how you can figure that out if you get a program that doesn't give you the right answer. And actually sort of the basic bottom line way to look at your code and see what's going on is to just print out certain things. So System.out.println is your friend. And so particularly in a loop, if something goes wrong inside a loop, you're going, what happened? And so what you might do is you might insert a print statement inside the loop to check the value of the loop counter, to check the value if you're computing a color, for example, to make sure that the values of the color are correct, etc., etc. In most loops, this is fine. When we're working with pictures, though, you have to be careful because there are so many pixels in each picture. We're talking hundreds of thousands of pixels. You don't need hundreds of thousands of lines of output. You could add a simple if statement in there that says if I is equal to, some multiple of 10,000 or 20,000 or even 100,000, then you'll print something out. And that will reduce the amount of printing you have to do, and it will probably get you the answer that you want. So I'm not going to give any examples of this right now, but this is a good way to start. Okay, so now let's move on and do some more examples. The first example we're going to do is how do you think you could take a color picture and turn it into a negative? Now, usually in the old days when there was real film, you took pictures on film, you developed the film, and the film itself became a negative of the picture. You then used a different process to actually print the picture on photographic paper and get what was called a positive of the picture. That doesn't work anymore in digital stuff because all you have is a file, and the file is actually a positive. But say just for interesting artistic value, you wanted a negative of the picture. How would you go about doing that? Well, first of all, of course, we'd need to change every pixel in the picture itself in order to create a negative. But then the question is, what value do you change the pixel to, right? Because the pixel has 3 different values in it, a red, green, and a blue component. What values would you change those to? I'll give you a second to think about that, and then we'll move on. All right, so if you've thought about that, one way to do that, and the way that we're going to do it is we can subtract the current value from 255 for red and green and blue. Because in a sense, since 255 is the largest possible value, if you take the current value of red and subtract it from 255, you'll get a number which is, in a sense, the inverse or the negative of the current red component. And the same thing with green and blue. So what we do is you get the array of pixels. You'll have to do a loop because you're doing all of the pixels. Get a single pixel. Set the red value to 255 minus the current red value. Set the blue to 255 minus the current blue. The green to 255 minus the current green. Increment the index and go back to step 3 and do this again several 100,000 times. So let's see what this looks like in BlueJ. Okay. And I just happen to have something written up in BlueJ here. So here's my class. The main, again, is only really used to create the picture itself. Notice I'm now creating the picture just using a single statement. I've embedded the file chooser.pickafile into the constructor for the picture, because file chooser returns a string, and that's what the picture constructor wants, is a string. So we're good. And then I'm going to show the picture, and then we'll, in this case, we'll negate the picture and wait a couple of seconds and then repaint so that you can see what happens. And so we said that the method for negating was to get all the pixels in the picture, and we can do that by using the getPixels method. We'll need 3 values, a red, green, and a blue value. Notice that in Java, you don't have to have separate line for each variable. You can separate them by commas, and then you can even initialize them all at the same time to one value. Then we're going to enter our loop, and now this is the only piece of Java that we're going to talk about in this video. And this is a new kind of a loop. It's called a for each loop. And what the for each loop does is it extracts one element at a time from a list, and then it uses that element from the list in the body of the for loop, and then it goes back and it gets the next element. And it starts at the very beginning of the list and it goes to the end. So it only works on the entire list. It's only good if you want to do something on an entire list. And so there'll be cases that we'll come up with in the next week or two where we want to do something on only part of a list, and we can't use for each there. But in this case, because we are doing something on the entire list of pixels, we can use it. Now the syntax for the for loop, the for each loop looks like this. You have to tell it what kind of item there is, and so we have our item in our list are all pixels. You have to give the item that you're going to extract a name. I decided just to call it PX. And then you have to tell it which list you're going to draw the L items from. And so we have this array of pixels. And so we're going to take an individual pixel from the array, call it PX, and we're going to do that for the entire array. Notice the colon here. The colon is required to separate the name of the item from the name of the collection of items. In our case, it's an array. So once we get a particular pixel, we're going to get the red value of that pixel and subtract it from 255. We'll get the green and subtract. We'll get the blue and subtract. We then have 3 values that should be the negative for us. We'll then use those 3 values and create a new color. So we're going to use the color constructor to create a brand new color, and it'll be the new red, green, and blue values, and we'll call our new color my new color, and then we'll just set the color of the pixel. So we'll change the color of the pixel again, and then we'll go and do this a gazillion times depending on the size of the picture. Okay, and that's all there is to it. So let's look at this. Let me compile, and then let's execute main. And we should pop up here, and we'll go to Dropbox, click, click, and we'll find media sources, click, click. And then let's see, what good picture should we do? How about if we look at me? I have a picture in here. So there's a picture, 1, 2, pow! All of a sudden, it's a negative. Okay, and it actually looks like the pictures that you've seen of a negative of a regular film picture. Notice my teeth, which were mostly white, are now mostly black. My glasses, which were dark, are now mostly light. You can see my eyes, and you can actually even see the iris in there. My hair, which is mostly gray, is still mostly gray because it just goes the other way. And so that's pretty cool. Let's do another one. I like those pictures. I think they're just interesting to look at. Oh, that's right. This is the one where we have to reset the Java virtual machine. Thunk. Okay. Try it again. We'll do that. We'll come here. We'll go here. Thunk, thunk. Go to media sources. Thunk, thunk. And we'll look for another one. Oh, here's a picture of some Greek ruins. Let's see how that goes. Greek ruins, negative of the Greek ruins. So the negative, it gives you some interesting effects. And so this could be something that you could use to create different collages or do other interesting visual effects. So, all right. Let's move on to another example then. How about changing a color picture to grayscale? Okay. No, not that way. We're not going to do that. No. Different class. Okay, so how about changing a picture from color to grayscale? So what do we need to do? So we have a color picture, and we would like to turn it into a grayscale picture. Okay? There are 256 possible values in each color component. And we know that different shades of gray all have the same thing in common, that the red, green, and blue color components are identical. So 50, 50, 50 is a shade of dark gray. 200, 200, 200 is a shade of light gray. So that means there are 256 different shades of gray from 0 to 255. And the question is, how do we convert one of the 16 million colors into a shade of gray? I'll let you think about that for a second. All right, we're back. So here's a grayscale picture of Alan Turing. Notice his hair is darkish, it's black. Notice the background is white, but it shades into gray. Notice his face has different shades of gray. His tie looks black, but his shirt is a very light gray. His jacket is a darker gray. Miles Davis, same thing. His skin is different shades of gray. His shirt is a little bit off-white. The sheet music's a little bit whiter. The trumpet has different shades of gray in it. The only color is there. Oh, by the way, we'll be able to do this soon. So there's different. These are both black. They're typically called black and white pictures, but they're really grayscale. Okay, and so the question is, how, if we had a color picture, for example, of Miles Davis, how could we convert that into this type of grayscale? I used to do black and white photography. I always loved black and white photography because you could get lots of contrast, lots of interesting pictures. So changing to grayscale. Grayscale ranges from black to white. The red, green, and blue values are the same. And how do we change the color into the correct shade of gray? We could, of course, just choose a shade of gray, but that would be not good. It wouldn't look realistic. And so the question is, what number can we use for all three values? And the answer is, whoops, where are we going? it won't advance. Can we advance? Oh no, up. There we are. There. We can average the colors. So we can take red, green, and blue, add them together, and then divide by 3. So for example, if we have a color that's very heavily blue, but it still has some red and green in it, we could add these 3 numbers together, and we could get an average of 90, which is sort of a medium gray here, right? So this color, which has lots of blue in it, would morph into this medium gray color. And so what does the grayscale algorithm look like? We get the array of pixels. We start the loop. We get the pixel. This looks distressingly familiar. Then we calculate the average intensity of the current values by computing their average. We set the red value to the average, set the blue value, set the green value, and then increment and go back and do this again. All right? So let's go to the videotape and look at that. So here was our negate. So here is how we do grayscale. It's practically the same algorithm as negate, except of course for the loop body. All right. So in this case, when we call grayscale, we'll grab all of the pixels from the picture. We'll have a value called gray that will initially be 0. And then for each pixel, this time we're back to using a traditional loop. For each index into the pixel array, starting at 0 and going up to pixels.length -1, we'll grab a pixel from the array. It's already an array of pixels. We just have to grab one. We then compute the intensity of the pixel value, which we're calling the average. And so it's going to be pixel.getRed plus pixel.getGreen plus pixel.getBlue divided by 3. This actually will be an integer division, so this is strictly not necessary, the cast. And then we set the pixel color to gray, gray, gray. And we should end up with a nice grayscale picture. So let's go back up here. We'll comment out the negate, and we'll open up the grayscale. And we'll do the same thing we did before. We'll compile. That worked. We'll come here. And we'll grab a picture. Media sources. Let's see. Oh, I had a picture of flowers here. So if we look at the flowers, there's the flowers. 1, 2, poof. And now it's a grayscale picture. It's an old-timey black and white picture of a garden, which is, of course, as far as a garden is concerned, not as satisfying as the color picture. But we can do another one. Once again, we'll pick main. We'll go here. We'll go to media sources. We'll go, let's see, look at Knox picks. How about Professor Hoffman? There's Professor Hoffman in her office, and poof, there's Professor Hoffman in black and white in her office. Which actually looks pretty cool. So you can see that her shirt, which had some color in it, has changed color. The plants behind her in her office have changed color. She had color in her face, which is all now grayscale, and so that works pretty well. So that works okay. So one more example. And that is luminance. Now, it turns out that just taking the average is not the best way to change things into grayscale, because the way our eyes perceive the colors, we perceive blue to be darker than red and green, even when the same amount of light is reflected. So even in a room where there's the same amount of light everywhere, we'll think of a shade of blue as being darker than a shade of green or a shade of red that are next to it. And so we should take that into account and use less of the blue when we're trying to do grayscale. So here's another model that's called the luminance model that takes that into account. And so what it does is it weights green the highest because green we perceive as being very, very light. And then red, and then blue. We rate blue the very least because blue will overpower lots of things. So if we do that, then we can see a better picture, a better grayscale picture. So what we've done here is changed the grayscale method. So this one because we're going to be multiplying by doubles here, I've changed red, green, and blue values to doubles. And I have this variable called luminance, which is the equivalent of gray in the previous method. And so I have this method called grayscale with luminance. We grab all the pixels. We initialize the local variables here. This time we're going to use the for each loop again, just because to give you practice looking at it. And so what we're going to do is for each pixel, we'll get the red component and multiply the red component by 0.299. We'll get green and multiply it by 0.587. And we'll get blue and multiply it by 0.114. We will then add the three of them together. And because we've multiplied by numbers that are less than 1, we can consider this to be an average as well. We're just using different weights for each one of the color components. So we'll add those together, convert it back into an int, and then stuff it into the luminance. And then make our new color. Notice that we can do this all in one line as well. Luminance, luminance, luminance. It's going to be gray of some shade. And it should be better. Now the question is whether we're going to be able to see whether it's better or not. And that'll be sort of up to you. And I think that's what we called the method. Let's go down here and make sure. And yes, it says grayscale with luminance. Okay. And so if we compile, good. We can must not have killed the Java virtual machine. Kill the Java virtual machine. Start again. Okay, Dropbox. Thunk, thunk. Media sources. Thunk, thunk. Let's do. I've got a blue. Don't I have a blue motorcycle? Oh no, I don't have a blue motorcycle. I have a Greek temple somewhere. Ooh, how about a red door? Why not? Oh, red motorcycle. Never mind. Red motorcycle. 3, 2, thunk. Okay, and so this gives us nice, interesting shades of gray. The green gets to be a little bit darker. The red gets to be a nice even shade. There isn't much blue in this picture. We can look for another picture that has blue in it. But let's actually do this one again in using just grayscale to see if we can detect any difference. Shall we? So we'll go back into here. We'll comment that out and we'll use grayscale. And we'll try this again. And we'll go here, media sources, and we'll zip down to the red motorcycle. Here we are. Red, dunk. And it's hard to tell the difference. This grass is a little bit lighter. This is a little bit darker because of how the red is formed. But it looks I mean, to me anyway, the grayscale with luminance, the picture looks a little bit better. So, all right. So moving along from that, right. What about going to the extreme, okay? And instead of just changing a color picture to grayscale, if we change it to a picture with only two colors, period, black and white. So how would we do that? I'll give you a few seconds. And in fact, I'll give you even more than that, because I'll let you think about that overnight, and what we'll do is in class, when we come up to this, which I think should be Friday, we will write the code for black and white in class. So stay tuned to that. That's it for today. Thanks a lot. See you later.